before starting to read my paper, I want to do two preliminary remarks. So the first is my interest in computer vision arose during a mixed methods or digital humanities research project in which we applied very different methods of computer vision to images of climate change on the internet. And in the last module, we experimented with similarity algorithms based on, well, this pipeline, which you can read here, and also the convolutional neural networks to cluster several thousands of images by similarities. And this method also underlies this tool, which was developed in the same project. It's a viewer which we suggest for clustering the images of large databases. And for me, who was trained as an art historian, it was very exciting, but also astonishing to see that actually this idea of similarity, which is the driving force of art history and image comparison, is very well worked out by these systems. My second preliminary remark is that I'm coming from a background in media history and art history, and I have been looking into the history of vision and especially the history of the gaze and the observer for a long time. And so these two topics come together in my talk. The history of computer vision and the historical development of concepts of machine vision is only available in parts. David Marr was a British neuroscientist with training in psychology and mathematics alike. And he went later to MIT in the 1970s. And therefore, I'm sorry, I will move this talk also to the United States. His book Vision, which is already 40 years old, is regarded today as a milestone in the history of today's computer vision based on convolutional neural networks, that is staggered levels of neural networks, as they have become so successful in the last decade for computer vision. So there are computer vision engineers talking about this book and David Marr as the holy grail of biologically inspired computer research vision. And so Marr's book is an example for how not physics or computer science, but the perspective of neuroscience and psychology help to envision computer vision. And of course, I could have also chosen other researchers here, but I will take him as a test case for this approach. This book, Vision, which you can see the cover here, summarized Marr's studies in the 1970s, and it only was published in 1982 because he died aged 35 in the year 1980 already. For humanities scholars interested in a history of vision and the concepts behind it, the close connection of computer science and brain research in this field as early as in the 1970s is significant. We already heard that the field of cybernetics used to be so productive because of its radical interdisciplinarity. And this interdisciplinarity was established, let's say, already with the beginning of the field. Oswald Wiener, in his famous book, already had demonstrated or had decided to abolish boundary struggles but use the technical terms of information theory, not only for machines, but for animals alike and vice versa, and to summarize all their functions in only one theory. So the discourse on the question of human versus technical intelligence was blurred from the outset. And so I would say it is precisely from this blurring of boundaries that the success of machine vision during years arose. And I will come back to this point at the end of my talk. Therefore, anyone reading Marr's book with a preconceived question in his or her head as to what extent the information theory of the computer is here the godfather of human vision, or vice versa, will get lost in a spiral where you cannot tell where metaphors begin and end. And this is also why I put this quote up here. So I have three parts, in my talk, the first part is on Mar's idea of vision. The second part is about a short idea on the disorder of machine vision and the phenomenology of machine vision. And then the third part, I will discuss a little bit the question of the analogy of vision and machine vision. Old theories of vision, such as the eye as a mirror or vision as camera obscura, but also seeing as perspective projection, were not the ones that were carried forward here in computer vision, as we are talking about today. Neither the field of neuroscience nor the field of computer vision. It was not the Cartesian geometric space of the objects that, as it is so important for the art of designing perspectives in pictures, that led on here. We could say CNN's digital eye doesn't need geometry in the first place at all. David Marr had been working, and here I give you the examples. Forget to show this screen so that we can think about a history of the theory of vision along these models. Marr had been working on neuroscientific fundamentals of vision since the 1970s in the Artificial Intelligence Laboratory at MIT. I'm showing you Stanford here, together with many colleagues. This is where his knowledge on human vision systematically was connected with computational theory, but also with experiments of modeling human vision in hardware, while at the same time projects such as block swirls, ARC, and robotic cube stacking experiments were applied in the laboratory. And I just imagine the MIT laboratory also using the hallways as a laboratory for object detection. So what did Marr do at MIT? In the first place, he changed the entry point of the approach by distinguishing 3 levels of explanation. They later became known as the Marr paradigm. And he promoted the idea that complex systems should be understood at 3 different levels. And this you can see in the sketch with the bird. At first, you have to tackle the problem specification. Only then you think about algorithms, and finally, you approach biological or technical implementation. In the context of machine learning and statistics, this approach became an important framework that is often used when describing probabilistic models of cognition and perceptual systems. The second important point of Marr's book lies in the notion of different levels of perception. And this new concept of vision, we are still talking about human vision here, had been developed by David Hubel and Thorsten Wiesel, both neurophysiologists who had explored visual processing in experiments with cats' brains. And note, so this is biology. By studying how neurons react to various stimuli, the team observed that vision works hierarchical and that there are different types of cells for all levels. Many of you will know. Neurons detect simple features like edges, then feed into more complex features like shapes, and then eventually feed into more complex visual representations. And this is the idea Marr took up for his further development. And I want to make another statement here. For me, as a person looking at images from an art historian and pictorial science, Bildwissenschaft background, when I read the Marr book, it was quite challenging because it is central for my field of studies to distinguish pictures from images and to distinguish images and pictures in turn from perceptions of the environment. And this is because one is 2-dimensional, the second is in the mind, and the third is 3-dimensional perceived reality. When reading Marr's book, one has to abandon this distinction. When you are exploring image processing in the brain, the distinction between images and 3D perceptions is irrelevant. And this is because the complexity of the 3-dimensional world can be successfully recreated from 2-dimensional images in stereoscopic vision. The concept of different levels of perception became fundamental for Mar's concept on the primal sketch. At the core of this concept, the primal sketch, is edge detection. And this meant a profoundly different concept of process of seeing. Seeing an object proceeds primarily as a recognition of lights and shadows. So it's not at all about the shape or the form of an object and their significant patterns. The seeing system recognizes the objects based on the reflections and shading alone. And this is done via the detection of varying intensities. Mar calls the significant points in an image which are detected the zero crossings, as I can show you in this picture. So the curves go through the zero line, and this is the intensity change of the zero crossings. In the graph, the changes of intensities are shown as the intersections of the amplitude with a zero line. And then I try to do this pipeline, let's say, again, but with different images. So he differentiates that different levels. The lowest layer of perception, of perceiving an image, is the primal sketch, a representation of the retinal image that makes explicit the size and the disposition of the image intensities. And then there's something called the 2.5D sketch. This makes explicit descriptions of the boundaries that exist in the image. Sorry, this is still the primal sketch. The 2.5D sketch contains local surface orientation and depth. So you see little arrows pointing to directions here. And the 3D model gives an idea of the volumetric shape. And by the way, if we would go deeper into the history of the test images by Mar, it's quite interesting what images he uses to make explicit his ideas. It's Henry Moore's statue, which actually is placed on the MIT park in the MIT area. And also, this is something a lot of people do in technical innovation. They use photographs of historical persons, in this case, Abraham Lincoln's famous picture. I will skip this. So the important thing is that actually Mar has a very different idea of looking than compared to the historical ones, which thought of vision not as just intensity detection, but more in geometrical ideas. And I will now come to the second part. Yeah, I just wanted to show you these images that actually how the process went on, and when computer vision started to use more and more data, like the Imagenet, with a lot of data from different pictures, and so they could get successful with machine learning, and with also showing cats in this way and detecting cats with statistical methods. For example, here you can see that this neural network, it detects convolutional neural network. It recognizes an Egyptian cat with 0.27 and not so much a tabby or a Siberian husky, and it's also not a mouse or a computer keyboard. And this is actually what the neural networks can do today. So I would now come to my second part of this talk. The question if what visual dysfunction as an approach to a phenomenology of computer vision might tell us. And this is very speculative now, because I would like to know, now that computer vision is so successful, what kind of vision appears in the disturbances of computer vision based on artificial neural networks? That is, where does it not work? What after images, what visual disturbances does computer vision have? What blind spots? Are there also basal stimuli or blurs or disturbing flickering or flashing like the human eye has? What pre-existing grid do these CNN already bring with them? And so I propose to approach this question of computer vision through phenomenology of computer vision. And actually to ask about the invisibility of the medium or the invisibility of the processes of machine vision is a very familiar take of media theory. And I will quote Sibylle Krämer here, who is also in the audience. She once wrote that media act like window panes. The more transparent they remain, the more inconspicuously they remain below the threshold of our attention, the better they do justice to their task. Only in the noise, however, which is in the disturbance or even the collapse of their smooth surface, does the medium bring itself to mind. The undistorted message, or on the other hand, makes the medium almost invisible. So disturbance is a method to make visible these smooth operations. So to make visible the disturbances of the convolutional neural network machine vision, for example. And now I will just go through the slides very briefly because I do not have the time. So since the 18th century, one way to learn about perception has been to do so through the disorder of the sentence, from Blindness, for example, that is ex negativo. This is a famous book and philosopher who did that. And somebody like Purkinje, for example, a physicist from the around 1900, he repeatedly had pressed his eyes in an experiment and exposed his gaze to lurid flashes in order to decipher the functioning of the eye from the image impressions that caused these after images. So this is also a typical way to actually do research on the organ itself. Or the famous rotating discs or screens from Hermann von Helmholtz for measuring the visual velocity. So there are all these images to actually test human vision. And so I was thinking, how would we test computer vision and what would it tell us? And I found this experiment in a series of articles, What Do Your Computers See? By software developer and back then Google employee, Osinga. He wanted to do these experiments. So he asked, how do we prod a neural net with an electrode? And in the looped video, which is the result of this probe, you can see small herring hook-shaped shapes appear, which the network recognizes in the noise. And so a noisy image which has no information in it, and then still amplifies layer by layer, because this is what this network has learned. In a second experiment, you can, based on the same principle, Osinga connected and amplified different neurons in different layers of a CNN. And you can see here how the patterns become more and more complex from the lower levels to the higher levels, until they become these patterns, although in the input image, there hasn't been information at all. And of course, we could go into these deep dream algorithms, which based on similar ideas to make visible what actually the training images have been to for machine vision. Instead, I want to bring into sight this project by artist Sterling Crispin. This was an installation, for example, you could see it in Karlsruhe some years ago. And using the reverse engineering, and Adrian Lobe, a political scientist and author, stated about this, the algorithm, and this is what is disturbing, even mortifying about this experiment by Sterling Crispin, does not see us as humans, but as disfigured figures, as grimaces. So this is just the idea, like how would computer vision actually see a human being? And also we can see that the concept of making statistical statements about, we had this example, female or male, actually is based on a concept which is might not be comparable to what we think about vision at all. So I would come to my third part, which is a short part, which is the question, is this a metaphor? Is computer vision and machine vision, are they related to human vision by metaphor, or how can we think about this? And this idea of brain-like architectures, we tackled this in several talks already. And I would say that brain metaphors have a history, a long, long history. The study of perception has always been linked to metaphors and models, which makes the history of perception a parallel media history of metaphors. So as you can see here, Plato's wax-covered writing tablet, or the Diderot's silk loom, or Samuel Morse's telegraph network, wired like a network of nerves. The most up-to-date technical media in each case served as models for cognition and vice versa. They made consciousness, perception, sensory cognition, and the nerve conductions imaginable. Media scholar Friedrich Kittler quoted the poet and philosopher Jean-Marie Guyot, who wrote in 1880, "Thus the human brain has been compared to many different objects." And then he goes on the resemblance to the mechanical piano, the printing press, and most recently, the phonograph invented by Edison. The quote, "conclusion by analogy would possess in science a considerable importance," and this is Kittler again. "Indeed, perhaps analogy, insofar as it is the principle of induction, forms the basis of all physical and psychophysical sciences." And when reading the book Vision, I had to always actively recall to myself that Marr actually deals with the vision of a visual cortex. The publication deals with neural networking in the brain, but unfolds it as a general framework in terms of computer science. The relation of the two realms, wetware and hardware, is not just a metaphor, it's a structural analogy. And I would say it's an analogy model. And also we, of course, have to think about this relationship in the term of a simulation. That is the modeling of a dynamic system with the help of a computer, for example. Analogy is a source of insight and knowledge for science. It is extremely valuable heuristically, especially for accurately characterizing the similarity of systems characterized by structural analogy. However, model and original, simulation and the brain are never identical, because unknown parts in the model have to be supplemented on the basis of hypothetical assumptions. The conclusion by analogy is, if the model functions in a certain way under given conditions, the original must also show at least a similar functioning under the same conditions. And I found interesting books and articles written about this idea and metaphor in the history of psychology. We've seen this cover yesterday already, but also the evolution of mental metaphors in psychologies. And so we could say from metaphors to Analogiemodelle, analog models, to simulation. And Ernst Mach, in his book Erkenntnis und Irrtum, Insight and Error, also wrote about this in 1905. He says, similarity and analogy are leitmotifs of research. A deeper lying similarity, or one could also call them an abstract similarity. And in one of the chapters on the metaphors in psychology, Karl Pribram wrote that I find it useful to distinguish between metaphor, the large concern of this volume, and analogy, a way of reasoning about metaphors, and model, a precise coupling of an organization of data to another mode of organization, such as a mathematical formulation. And I think it's important to differentiate in this regard in order to understand why Marr's book became so fascinating for machine vision and programmers after on, although he was explaining human vision in the first place in his book. And of course, what are the problems of mistaking analogies and metaphors for reality? This is always the question. We conceive of ourselves in the image of our machines. This might be a problem. I will skip this slide. Yeah, but just a sentence on the top, which I can't read because of the technical interface of Zoom. The problem, the power of, let's see, where did I write it down? So I will just suggest to think of a technological other, which might also exceed, not in the way of optimizing or making better human perception, human vision, but by creating a different form of intelligence, of a technological other. And I show you these Jakob von Uexküll images because this is similar to plant cognition and also the idea of animals and how they perceive their environments. Thank you very much.